So let's practice this with this example. So the function given to us is e raised to the power x, and our center a is 0. We are going to find a third order polynomial to approximate the function at x equals 0.5. That means slightly away from the center 0. And that means finding the polynomial at 0.5. So let's start. So let's first review the formula. So the main thing is that we have to find these coefficients. And a is 0, so therefore you want this term would be 0. So the function f of x is e raised to the power x. And at x equals a, which is 0, we get e raised to the power 0, which is 1. F prime of x is derivative of this, which is again e raised to the power x. And therefore at a, that means f prime at a is also 1. Now in this particular case, obviously it's pretty straightforward because all the derivatives are e raised to the power x. So f double prime at a is also 1. And since we have to find p3, I have to go till the third derivative. So the third derivative at my center a, which is 0, is 1. Now let's remember what p3 is. So let's write it out. So that is f of a plus f prime at a times x minus a, but a is 0, so it's at x multiplied by x, plus f double prime over 2 factorial times x squared, plus the third derivative at a over 3 factorial times x cubed. Now this comes straight from here. We are going till the third derivative, till x cubed. So let's plug in all the things that we have found. F of a was this, so this is 1, plus f prime at a, which is 1, so that's 1 times x, plus f double prime at a is also 1 over 2 factorial x squared plus 1 over 3 factorial times x cubed. So writing it nicely, you get 1 plus x squared over 2 factorial plus x cubed over 3 factorial. So this is the third order polynomial which approximates e raised to the power x near the center, which is 0. Okay, so now we are going to use this to approximate the function at 0.5. So that means find this polynomial at 0.5. So p3 at 0.5 is stick in 0.5 at x, wherever you see x. So 0.5 plus 0.5 squared over 2 factorial plus 0.5 cube over 3 factorial, and use your calculator. Keep certain number of decimals. Let's suppose we agree to keep 6 decimals, so I'm going to get 1.645833. So that is my approximation. Okay, by the way, we'll see it's very soon, but the exact value is obviously f of 0.5, which is e to the power 0.5, and you can use your calculator to find it, and you would get 1.6487 721. Very close. We'll see that in few minutes. Okay, now the B part of the question is, so this was A part. We are supposed to guess what is P5 of x and then use that to approximate the function at 0.5, which means finding P5 at 0.5. Now guessing in this particular case is not difficult at all. If P3 of x was this, then P5 would be 1 plus x squared over 2 factorial. So keep this pattern till the 5th power of x. So we get this. Now the question wants us to find at x equals 0.5. So we are still trying to approximate f of 0.5 by using P5. So you stick in 0.5 for x here, and it'll take few minutes to do the arithmetic of using your calculator. If you do it, you're going to get 1.648698. So this is P5 at 0.5. Now the C part of the question says compare the above result with the exact value, find the percentage error, and what are your conclusions. So this is our exact value, so let's compare it. So let's make a table so that we can compare these values. Okay, so let's make a table. So this is n. So first n was 3, so P3 at 0.5 was 1.645833. When n was 5, then P5 was 1.648698. The exact value f of 0.5, this is the exact using the calculator, is 1.648721. Obviously it's the same for this as well. So now let's find the percentage error, which means basically I'm going to take f of 0.5 and subtract Pn at 0.5 and divide it by f of 1.5. So what is the error in this? So if I do it, I get 0.001752. So that is approximately, let's say, 0.1752%. That's not bad at all. And if n is 5, then the percentage error becomes really small. 0.000011411. So that is like 0.00114%. So clearly the error goes down as n increases. That means the approximation improves as you take more and more terms. Then part D, we have to find the approximation at x equals 2. So we're going to approximate the function at x equals 2. That means we're going to find P3 at 2 and P5 at 2 and then compare with the exact value. So how much is the error and what do we conclude? So let's do that now. So first I have to find P3 at 2. So P3 at 2 means my P3 was right here, 1 plus x squared over 2 factorial, etc. So I will get 1 plus 2 squared over 2 factorial plus 2 cube over 3 factorial. So when I do this arithmetic, I'm going to get 6.3333 like that. So this is my approximate value with the third order polynomial. Let's find P5 at 2. So I'm using more terms. So I do this stick in 2 there. And when I do it, I get I get 7.26666. Quite a bit of variation. The exact value is obviously e squared, and if we do that, we get 7.38905. Clearly, this is with n equals 3 is not good. This is little better, which we expected. As n increases, I'm going to get more and more exact value. That means better and better approximation. So we can again find the percentage error, so we can make our table exactly like before. N, Pn at 2, f of 2, the exact value. So when n was 3, I'm just rewriting these, it was 6.33333. When it was 5, it was 7.26666, so on. Exact value was 7.38905. This is the same. So percentage error. If you were to find it, for the first one it was 0.1428, which is like 14.28%, which is quite bad. And for NS5 we get 0.01656. So it's at least it's better. It's around 1.6%. So what is our conclusion? So the reason what is happening is, one thing is for sure, as n increases, the approximation is better. So approximation improves. But as x goes further away from the center, as x moves away from A, remember A was 0, and when x moves away from this, the approximation becomes worse. So approximation is poor. We'll come to this more mathematically very soon, but intuitively it makes sense, because if you remember, our approximation was at 0. So when you are at 0.5, you are pretty close. And so whatever polynomial we fitted here, so this is my Pn of x, and this is my f of x. This error is much smaller. But if I'm at 2, then the error increases. Let's practice another example. So this time my function is ln x, my center is 1, and we have to find P4 of x. So that means my n is 4. So I need to go till the fourth derivative. So the process is very similar. We start with the function. Then we find it at a, which is 1. So my function is ln x, and at 1 it's ln of 1, which is 0. Then we find the derivative, f prime of x, which is 1 over x. Which I can also write as x raised to the power negative 1. So at a equals 1, I have 1 over 1, so that is 1. Now I have to find the second derivative. So the derivative of x raised to the power negative 1 would be negative 1 x raised to the power negative 2. So f prime at 1 would be negative 1. This is f prime at 1, this is double prime. Then f triple prime, third derivative. So if you take the derivative of this, you're going to get 2x raised to the power minus 3. So the third derivative at 1 is 2. And we need the fourth derivative. So that would be negative 6 x raised to the power negative 4. Again, at 1, that would give me negative 6. Okay, now let's recall what P4 of x is. You should always write it out. That would be f of a plus f prime at a. Well, in this case we know a is 1, so we can write f of 1, f prime at 1 times x minus a, which means x minus 1, plus f double prime at 1 over 2 factorial times x minus 1 squared, plus and so on till the fourth one. Now, well, let's write it. Plus f triple prime at 1 over 3 factorial times x minus 1 cube plus f fourth derivative at 1 over 4 factorial times x minus 1 to the power 4. Okay, now we have all the values, so let's substitute. F of 1 was 0 plus derivative was 1, so 1 times x minus 1. Then the next one is negative 1 over 2 factorial times x minus 1 squared. Then plus 2 times x minus 1 cube, 2 comes from here, over 3 factorial. And then minus 6 minus 6 comes from here, over 4 factorial times x minus 1 to the power 4. Okay, now remember 3 factorial is how much? 6, and this is 24. So very convenient. This becomes x minus 1 minus x minus 1 squared over 2. 2 factorial is 2. Then this is 6 and there's a 2 here, so that cancels and I get 3. So x minus 1 cube over 3. This is 24 and here is 6. 6 and 24 leaves me with 4. So minus x minus 1 to the power 4 over 4. So this is P4 of x. Okay, one more practice problem. So this time my function is this, center is 0, and we have to find fourth order polynomial, Taylor polynomial, and because the center is 0, it's also called Maclaurin's polynomial. So again, let's start with f of x which is 1 over 1 minus x, which I can write as 1 minus x to the power negative 1. Now at a equals 0, so that means f of 0, what do I get? Simply 1. Derivative, first derivative. So the derivative would be, now I'll need a chain rule here, so be careful, negative 1, 1 minus x raised to the power negative 2 times negative 1. So that means f prime at 0 would be again 1. Because you have a negative 1 and another negative 1. So that gives me 1. Now second derivative. Now let's write this. This is what? 1 minus x to the power minus 2. So I'm going to get negative 2, 1 minus x raised to the power negative 3, and then I get a negative 1 because of the chain rule. So f double prime at 0 is 2. Third derivative. So I have a 2, and then I get a negative 3, 1 minus x raised to the power negative 4, and then a negative 1 because of the chain rule. So the third derivative at 0 is 2 times negative 3 is negative 6, and then negative 1, so that makes it 6. And the fourth derivative is going to be, so I already have a 6, then I get a negative 4, and 1 minus x to the power negative 5, and a negative 1. So the fourth derivative at 0 is 24. So what is my P4 at x when the center is 0? So that would be f of 0 plus f prime at 0 times x plus f double prime at 0 times x squared. Third derivative, x cube. Oh, there's a 2 factorial here. There's a 3 factorial here. And the fourth derivative over 4 factorial x to the power 4. Okay, so let's substitute. So I get 1 plus 1x plus 2 over 2 factorial times x squared plus 6 over 3 factorial times x cube plus 24 over 4 factorial x4. So I have 1 plus x. Now 2 and 2 factorial are same, so you get plus x squared. 6 and 3 factorial are same, so plus x cube plus x to the power 4. So this is my P4 for this function. So this is very nice and very important. We'll see it again later on further down the chapter. Finally, we are going to study what is called the remainder in a Taylor polynomial. Now, Taylor polynomial is a good approximation of f of x near the center A. But we would like to know how good is this approximation. In other words, can we find or estimate the error in this approximation? So what that means is we agree that that the function f of x is approximated by the Taylor polynomial. Now the question is it possible to make it equal? I mean, if they were to be equal to this, then there must be some error, some remainder left over here, and that is called the remainder. Because if this is an approximation, that means some little amount is left, and that we add on and call it a remainder. So this is the error, or also called the remainder. So let's see. This error is called the remainder of the Taylor polynomial at x. So we are defining this exactly what I just explained. Let Pn be the Taylor's polynomial of order n. The remainder in using Pn to approximate f. In other words, the error in making that approximation is given by this. That means the remainder is the exact value minus the approximation. This is exactly what this is saying. But then the question is, can we find or estimate this remainder? Yes, we can, and that is from this Taylor's theorem. So what does this theorem say? It looks fancy, but pay attention. So let f be have continuous derivatives up to n plus 1 order. So suppose n is 5, you are using p5, then what it's saying is that up to the 6th order derivative exists and is continuous. Not a problem. So for all x in that interval around a, f is Pn plus Rn. Yes, I mean that's what the definition of Rn is, where Pn is the nth order Taylor polynomial centered at a, and the remainder then is given by this result. So what it says is that the remainder would be the n plus first derivative at c, where c is some point between x and a, divided by n plus 1 factorial times x minus a raised to the power n plus 1. So this looks very similar to our earlier notation. The only catch is that it is at some point c. So the first part of this is basically repetitive. This we know is repetitive and is defining what we already know. Then there is the formula for Rn. So I just explained this formula for Rn. It looks complicated basically because of this n plus 1 thing that's written there. But actually it does not help us compute the remainder. It tells us what it looks like, but it does not tell us. Why? Because just tells that there is a point C where this formula could be used. But of course, we don't know what that point C is. So there is some point C, but what is this C? We don't know. However, more important about this theorem is these two things that it tells us. So it tells us two things that we have observed earlier. If you look at the formula for Rn in the box above, you will notice two things. So those two things are, as n goes to infinity, so as n goes to infinity, the denominator goes to infinity. So this n plus 1 factorial, this is a factorial. So this goes to infinity very fast. And therefore, the remainder goes to 0. Which means the Taylor polynomial Pn of x is becoming more accurate because the remainder is going to 0. Second, as x gets nearer to a, that means the nearer you are to your center, the numerator goes to 0, obviously because the numerator has x minus a in it. So x minus a will be 0, therefore your remainder will go to 0. So that means that the Taylor polynomial is becoming more accurate as you go nearer to a. We are not going to do any computational problem in this particular section at this time, but you notice how the remainder can be computed if we knew the point C, but it tells us these two important results.